We're going to start off by looking at doing inference for one categorical variable. And one categorical variables will have a one-way table. It'll just have one variable, and it'll have the counts for that variable. And what we can do is we can do a chi-squared goodness of fit test. And what this test does is it tests how well the observed data fits the expected data. The hypotheses, you should have gotten this from your textbook. They will look like this. Let's see if I can find them quickly here. So they'll look like this. So the hypotheses, there's two ways you could write them. The null can say the specified distribution of the categorical variable is correct. The alternative can say the specified distribution of the categorical variable is not correct. Obviously, these would be in context. The other way to do it is to write like the null saying P1 is supposed to be equal to this, P2 is equal to this, and so on. The alternative we can say at least one of the above is incorrect. So either way, you can go with that. When you calculate the expected counts, I'll show you that in a problem, but the expected counts are under the assumption that the null is true. Do you round them? No. Because they're just expected counts. Your test statistic, so it's like a kind of a fancy x squared. It's the sum of the observed minus the expected squared over the expected. Is it on the formula sheet? Yep. So what does it measure? It just measures how far away are the observed and expected in a ratio against the expected. Your chi-square distribution, it is not a normal curve. It's a right-tailed, it's a right-skewed distribution. And depending on the degrees of freedom, it changes the shape. So here's the degrees of freedom. Let's see if we can do this here. Oops, this is going to start there. So here's the degrees of freedom of 1 for the chi-square distribution. There's 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8, there's 9, there's 10. So the chi-square distribution, it just keeps, it's right-tailed, it's right-skewed. It'll start off over here. As the degrees of freedom increase, it goes over here. The degrees of freedom for this test will be different than we've seen in the past. It will be the number of categories minus 1. There's calculator commands, but I do also want to show you how to do the p-value using the chi-CDF command, chi-square CDF. I believe that it's still number 8. So second distribution, if it's not, just look at the chi-squared CDF. You want your lower bound, your upper bound, your degrees of freedom. And again, so like in this example, if the test statistic was 10, the categories is 16, so the degrees of freedom would be 16 minus 1. So that's where I came up with the 15. All right, the chi-squared test, since it's always a right-skewed distribution and it's a squared test statistic, so this answer will never be negative. When the observed and expected are close to each other, the test statistic is small. If the observed and expected are far away from each other, the test statistic is bigger. So it always goes in that direction. So when you find a p-value, it'll always be in the right tail. So basically, the upper bound is always going to be positive infinity. All right, so we talked a little bit about the hypotheses, how we write those. So the method is inference. It's a chi-squared goodness of fit test. Random is our usual check. The large sample check. So this one we don't have a normal check. In order for that test statistic back here, this one right here, to follow the chi-squared shape, you are supposed to have the expected counts are to be at least 5. It doesn't have to be the observed, just the expected counts. So, and I'll show you how to find the expected counts when we get to the example. Are the observations independent? So this is our same check. Here's our test statistic. I just showed you how to find the p-value. There is a goodness of fit test on some of the calculators. On the ones in class we have them, and the older ones they don't. This looks the same as it's always looked. All right, when we do this example, I'm going to show you both the formula and the calculator because some of you might not have this command. All right, so we've got this book, Outliers, then we have Malcolm Gladwell. He suggests that a hockey player's birth month has a big influence on his chance to make it to the high levels of the game. So basically, he's saying that more people are going to be from the earlier part of the year. So he looks at a random sample of 80 National Hockey League players. He's got 32 born in the first quarter, 20 in the second quarter, 16 in the third quarter, and 12 in the fourth quarter. So these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year. So like I told you before, that hypotheses, you can write it either way. So we can say the specified distribution is correct, or we can write it using the P's. So if I go back here and I look, so the first time I wrote it, the birthdays of the NHL players are uniformly distributed across the quarters. And so that's like doing it like this way. And then the not's always in the HA. So then I would say in the HA, the birthdays of NHL players are not uniformly distributed across the quarters. If you want to write it in symbols, so HO, P1 equal P2 equal P3 equal P4. So if it's uniformly distributed, each of those proportions will be equal to 1/4. So P number is the proportions of births in that quarter. And then I would just say, alternative would say at least one of the P's is incorrect. It's a chi-squared goodness of fit test. It's random. It says he took a random sample. All right, the expected counts. So there's 80 players here. And if we expect it to be uniformly distributed, then 80 divided by 4 gives me 20. So I expect 20 in each quarter, and that is at least 5. For the independent check, so we only have one sample again. So there must be at least 800 NHL players in 2009-2010. There were actually 879, so that check is good. All right, when we calculate the test statistics, so the way this is going to work, so I'll show you there's 2 ways to do it. You type everything in list 1, so you type the observed in list 1, my expected are the 20, oops, so I want to type the expected in that list 3. Or list 2. What I'm going to do in list 3 is I'm going to actually find that test statistic so that it's always the observed. So my observed are in L1 minus the expected. My expected are in L2. And that gets squared. Again, if we didn't square it, when we added them all up, it would be 0. It's the same reason we square in the standard deviation. And then it's divided by my expected. So I'm just looking at the difference there, squaring the difference, and then dividing it. And then if I go back to my main screen, the test statistics, so what it is, it's the observed minus the expected squared over the expected, and then I need to add up all those things. So I need to add up this whole list. And I'm going to have the calculator add up list 3. And I get 11.2. So what's happening here, the way you write this here, so the book and the AP people all recommend that you write at least one of the components out. So that's what I'll expect in my test as well. So the chi-squared is equal to, so my first observed was 32 minus 20 squared over the 20 plus ... Now you could, if you want to write out all the rest of them, go for it, but you don't have to. When those are all added up, all those ... I get 11.2. So when everything here is added up, I get 11.2. To find my p-value, so my lower would be the 11.2. My upper will be the positive infinity. All right, the degrees of freedom. In this one, how many categories are there? There's 4 categories. We have 4 quarters. So I do 4 minus 1. So I get my 3. I hit paste, I hit enter, and there's that p-value I got right there. And then just write down your degrees of freedom. All right, so well, I'll come back here in a second. The p-value is less than alpha. So I picked up here alpha was going to be 0.05. Rejected than all. There is enough evidence to say the birth of the hockey players are not uniformly distributed. Sometimes you're asked to do a follow-up analysis and try to figure out, like, what is it that's causing you to reject? So if I go back here and I look at my list again, which one of these, remember I added all those up to get the 11.2, the test statistic, so which one of these has the biggest contribution? This one right here has the biggest contribution. So this is the first quarter, and that was what Gladwell was hypothesizing, was that more people on the team were from the first quarter. So it does seem that he is correct. There were 12 more players than expected. So I'm saying 12 more. I expected 20 if it was uniformly distributed. There was 12 more born in that first quarter of the year. All right, so the other way you could have done this test, you can go to stat, you can go over to tests, and it's D on this calculator. Now, even when you do this here in this calculator, you still had to have typed in list 1 and list 2, because you have to tell the calculator my observed are in list 1, my expected in list 2. And then the degrees of freedom, I'm going to have to just change that as well to the 3. And then I'm going to hit enter. So you're still not too much, I mean, it's just a faster way to do it. Not too much. You still have to show the same amount of work. This one I don't really change. So this isn't going to look any different if you use the calculator command. The CNTRB, this is the contribution. If you notice, these values are those values that I got in list 3. These are the ones that we're adding up. So these are the individual components of the test statistic before you add them all up to get the 11.2. So that's all that's happening there. When you look at this next problem, the other type of goodness of fit, so this was a goodness of fit in which the proportions were just all equal. We could also have a goodness of fit in which we're just saying that they're equal to some proposed distribution here. So like in this one, I did this one 2 different ways, but like in this one, it's not 1/4, 1/4, 1/4. So you can go ahead and look at that one. Then another thing that is different about this one are the expected counts. So you can't just do that divided by 5 because you're not expecting it to be uniformly distributed. The problem's saying up here I expect 19.1% to be in their 20s. So what I do is if my total is 1,048, I'm going to take that 19 times that 1048, and I get 20.168. And again, these are expected counts, so leave the decimal. So there's my first expected one. The next one, is 21.5, so then I need to carry that out as well the same way. And again, I'm looking to make sure that those are at least 5. But otherwise, you can either use list 3, do it individually, use the test, the goodness of fit test. No matter what you do, what you're going to have to show, the work you're going to have to show is going to look exactly the same. I'll leave this here for a second. Again, you also have those 2 options for the hypothesis test. You can do what I did in red, or you can do it in purple down here, like it is in purple here. And that is it.